Hi guys, how's it going? So today we're gonna be going through a research paper. So the research paper is learning to embed categorical features without embedding tables for recommendation systems. I won't lie, I pretty much like this paper a lot. It was by Google, mainly because I think it has to do with the fact of the challenges that I've came across, and also reading a lot of companies' use cases and their project. They raise the same pain point, which is around how do we kind of like embed high cardinality data. For instance, I think it was Uber. On their ETA project, they did mention that the embedding module took something like over 90% of their parameters, right? So the ByteDance also released their recommendation paper, whereby they also mentioned that the embedding tables took more memory, and it has to do with high cardinality data. We're talking about things like IDs. For instance, Amazon has I think 30 million product IDs. So products come and go, right? We create new products and like that, right? So how do we then handle them in production? Like we gonna put everything into like out of vocab, then that might actually degrade our performance there in production a little bit. But yeah, that's like the motivation, I think. So yeah, I think let's get into the paper. It's quite, I like the idea, and yeah, it's quite interesting overall. I thought it would be a good idea to kind of like walk you guys through embeddings. I know you might be knowing what embeddings are, but I think I wanna uh, kind of like give you this content from a more of a motivation perspective why we have to go through the paper. So yeah, I thought this might be a good idea. Anyway, we can think of like we have some sort of keys which are then pointing to these vector numbers here, which we know we call them embedding. So the point is that as we get something like puppy, we can actually go into our embedding table so that we can get a numerical representation of puppy, because of we work with numbers here. But looking at these from an NLP perspective, what we do is that we create what we call the vocab. So you can think of these as all the words that we know, like in our use case, right? So we store those words along with the indexes. So this helps us that if we get a sentence, for instance, like the quick fox jumped, we can easily be able to retrieve the index. For example, there is pointing to 1, quick is pointing to 178. Then we get those indexes. We're not supposed to pass this into the model yet. We need some sort of semantic meaning between these weights. So what we do is that we need a vector that represent these indexes, and this is what the that face does. We have a vector. Each index is now is pointing to vector. So for some of you might be asking, how did you get the vector? We could have trained the word using word to vec. So you can think of this as like we try to create a numerical representation of the weight, but in a way that captures the semantic meaning of these words. So by semantic, I mean like all the words that have a similar meaning are close together in like geometric space. That's what it means essentially. Now looking at this from a diagram or high level overview, how it works is that we get those index that I spoke about, then we try to index the embedding table to get the vectors or the embeddings of each word. Then now we have our sentence represented like this, like this is a word, this is a word, this is a word. Then we start applying these techniques in deep learning, where it could be averaging the embedding, or maybe could be doing a dot product or something like that. But that's that. So what could go wrong with this? What is the problem with this, doing something like this? The first problem is that the embedding could get huge, like it could get very huge. And this is because of we saw this with this vocab. We needed to index all the weights. So it's similar to product IDs. We need to embed all the product IDs, right? So this then raises the issue on the memory side of things. So the traditional techniques that have been used, like things like hashing, we can hash and map each index ID maybe to share specific a vector or something like that. So those techniques have been introduced. Um, so let's take an example at like how this thing can cost us. For example, I'm looking at Amazon. It's assuming that it has over like 80 million of product IDs. So let's say that on average, the token take some sort of like 10 Unicode character, and each one of that token is 2 byte. So we can take that 30 million product and multiply it by 10 token and multiply it by 2 byte. This is going to give us 600,000 KB, which equates to 0.6 gigabyte, so 0.6 half gigabyte. So it's quite a lot. Given that when we are in production, we always want to like have low latency. So how do we then come up with a technique to solve this problem, right? So this is what we're going to look in our paper. So given the fact that working with high cardinality features such as video ID could be expensive in terms of memory, and also given the fact that like many people create YouTube videos almost like every day, so we face the problem of like out of vocab. So what the author did was to introduce this framework called deep hash embedding, which aimed at actually replacing the embedding tables overall with the deep embedding network. So you can think of this network as it computes the embeddings on the fly. So it first encodes the feature value to a unique identifier vector with multiple hashing functions. Then it applies a deep neural network to convert the identifier vector to an embedding. So what you can think of this is that, let's say we have a product ID 3, then what we do is that we use multiple hashing functions to create a unique identifier vector. Then we take that unique identifier vector, we pass it through our deep neural network, which is basically going to give us the embedding vector. So comparing this with how we used to do it traditionally is that we will then have to create a one-hot encoder with like the dimensions of the product that we have. So if like we have 30 product IDs, then like the dimension will be like 30 million or so. Comparing it with this technique is that the dimensions here is very slow, is very small. Sorry about that. Then we need to, with this technique, is that we also need to do a lookup of 2 million by 32 dimensions so that we can produce an embeddings of 32 dimension. That's like the one hot encoder. So it's quite expensive, as you can see how many the dimensionality of this technique. So they do say that the encoding module is deterministic, meaning that even if you can give it the same ID, you're still gonna get the same representations of the embedding. And it's non-layerable and free of storage, while the embedding network is updated during training to learn embedding generation. So what motivated the author to actually go ahead with this technique was the fact that in recommendation systems, we face the problem of high vocabulary size. So unlike NLP, whereby the vocabulary of words can typically be less than 30k tokens, however, with like recommendation systems, for instance, you can have a video ID for YouTube instance. I think it could be like billions of video ID or something like that. So it's quite huge. And they also state that the nature of these features are dynamic. So unlike vocabulary of words that are relatively static, now words do not change, but then the vocabulary in recommendation systems could be highly dynamic. New users, new items enter the system on a daily basis, and stale items are gradually vanishing. And they also state that they face the highly skewed data distribution. So now we're going to look at the deep hashing embedding components. So it contains of two components, which is encoding and the decoding. I discussed this at the high level. So just a refresher, we said that the encoding is going to take an ID, then it's going to map this ID to a unique vector identifier. So it does this by actually using multiple hashing functions. So now what we want to discuss is that how do we then design a very good encoding? So they use the author said that the encoding should be able to produce a unique vector identifier. So if it does not do this, what will then happen is that some of the IDs will be mapped to a same vector identifier, which will then hit the model performance. So what they did to counterpart this problem was that they used multiple hashing functions, which we'll discuss that portion in the later stages. The second portion that they discussed was the equal similarity. So we can think of having the uniqueness is not enough, right? An example is a binary encoding, which uses the binary representation as the encoding integers. So let's say, for instance, we hash number 9 and we get this binary encoding. We hash number 8 and we get this binary encoding, which is more similar to 9. So 8 and 9 have the same binary encoding. But when you compare this to 7, they are totally different. It's 0, 1, 1, 1. So what they state that this essentially introduces what we call inductive bias. So 8 and 9 are more similar than 7. So this can be misleading to the subsequent decoding functions. So they believe that this is not supposed to be like this. So they also do state that the same problem occurs when we apply a double hashing functions. So whenever we use two hash functions to create a feature value, what happens is that if it happens that a feature value collides with another feature value, it will be considered more similar than those ones that do not collide. So this also introduces an inductive bias. So in order to avoid these issues, what is important is to ensure that the two encoded representation are equally similar, regardless of their actual similarity. So this actually may help us to avoid introducing any inductive bias that could lead to a misleading or inaccurate result. They also add that actually having a high dimensionality unique vector is quite important, especially when it comes to creating a unique identifier vector. So they state that a high dimensional space are often considered to be more separable. We believe the encoding dimension should be relatively high as well. So after considering all the good design of designing a good encoding scheme, essentially the author found that no existing scheme can be able to satisfy all the desired properties. So for instance, if we take a look at one-hot encoding, yes, it does meet the free embedding table properties, but then it fails to satisfy the equal similarity and high dimensionality properties. Therefore, the author was inspired to propose a new encoding functions which essentially uses universal hashing functions to map the feature value to a k-dimensional dense and real-valued encoding. As of now, the output of the encoding cannot be passed directly into the deep neural network. This is mainly that the output of these encodings are real-valued and they are normalized for numerical stability. So we need some sort of like a way to transform these output. So what the author did was to consider the uniform distribution and the Gaussian distribution. You can think of the uniform distribution as we try to normalize the output of the encoding to range between -1 and 1. And as the hashing values are evenly distributed, this approximates the uniform distribution reasonably well when we have a large M. On the other hand, the Gaussian distribution try to transform the obtained uniform distributed sample by applying the Box-Muller transform, which then converts the uniform distributed samples between -1 and 1 to a standard normal distribution of 0 and 1. So unlike other previous papers whereby they were limited to only a few hashing functions, the author decided to actually use multiple hashing functions, right? So they selected a very large K, which you can think of it as like a large hash functions. This is mainly because they wanted to satisfy the high dimensionality property. Not only that, by selecting large K, It enabled them to be able to obtain a more distinguishable high-dimensional encoding without storage overhead. And from a computational wise, they realized that the term complexity was O of k, and the calculation of each hashing is independent. Thus, it enabled them to like run parallelization across like hardware such as GPU or TPU. So now we're going to look at the decoding component of the deep embedding network. So the decoding embedding, essentially what it does is that it has to take the encoding vector and try to transform it to the embedding dimension. So it uses a very powerful deep neural network to model very complex transformations. They use deep neural network because the expressive universal function approximates as in nature. So since the embedding tables were the ones that used to kind of like capture all the embeddings, so what they did was that they trained the deep neural network to be the one that now memorizes all the informations, like all the IDs and stuff like that, in its weight. So they hoped that the hierarchical structure and non-linear activation enabled the deep neural network to express the embedding function more efficiently than the one-hot encoding. They also state that actually they choose the deep neural network instead of the wide and shallow network, mainly because they believe that they can actually be able to approximate the function with fewer parameters. As noted also by the author, they do state that we relied on hidden layer to memorize and compute embeddings on the fly. Some of the transformations that they did on the deep neural network was that they actually had to remove ReLU activation function. This is mainly because they expected that ReLU is not expressive enough, as these ReLU networks are piecewise linear functions. So they decided to use the mesh activation function, which according to the experience, they saw that it performs better than ReLU. They also said that we found that batch normalization can stabilize training and achieve better performance. However, regularization methods like dropout are not beneficial, which again verify the bottleneck of our embedding network is underfeeding. So yeah, I think those are the key takeaways. I'll say I really like it. Maybe some of you guys might be asking yourself. I also had the same question, which was that uh, wouldn't the deep neural network be expensive? Like in production with embedding tables, we have constant lookup, but now with deep neural network, how long will it take actually to produce an ID? Um, so if like we can use probably like maybe certain techniques to make sure that the neural network has like few weights, I think we can still get the millisecond computation. The second thing is that like the deep neural network does not have to grow, right? Its weight can be constant, unlike the embedding tables whereby the table can continue to grow as we get more IDs. So that's another feature that I like. But yeah, I think that's all into it. Um, yeah, thank you guys for tuning in, and yeah, I'll see you guys in the next one.